All right, hello there. In this lesson, we're going to talk about how we can use what we've learned about rational equations to write a rational equation and solve it to solve what we call river current problems or motion problems in general. One of the things that we use is the relationship between distance, rate, and time, which is distance equals rate times time. And we specifically use that in these problems we're going to talk about today, solving this equation for time. So if we take and divide both of the sides of the equation by rate, we arrive at this equation here. The time is equal to distance traveled divided by average rate of speed, or average rate of travel. Another thing that we need to understand about rate in these situations is how the water's direction affects the rate of an object on the water. So if we're looking at upstream, upstream is when the water is coming towards the object or person, and because of the force of the water, it actually, relationship-wise, slows down the rate of the object compared to what it can go under its own power. So when we're writing rate of an object upstream, we have to take the object's speed or rate under its own power and subtract the rate or average speed of the water. If we're looking at downstream, in downstream, the object and the water are going the same direction. So it's like the water's coming from behind and pushing the object a little bit. And so we have to write the rate in this situation as the object's speed or rate under its own power plus the water speed. All right, so let's take a look at this example. So in this example, it says that Abram rows 9 miles downstream in his canoe and then 3 miles upstream to find a hiking trail. So what we need to understand is that those are the distances for each direction. A table is a good way to organize the information, especially when you're first learning how to set up these problems. And so in the table, we find distance, rate, and time for each direction of travel. So 9 miles downstream would be the distance traveled downstream, which would go here. And the 3 miles upstream would be the distance traveled upstream, which would go there. Then we see that the trip takes him 2.3 hours. We have to understand that's the total amount of time that he was in motion, and we'll come back to that a little bit later and how we use that in the problem. Then next, it says that if Abram's average speed in still water is about 5 miles per hour, how fast is the river's current? This statement tells us two things. One, what we're trying to find, which is the speed of the river's current, call it C, and also Abram's average speed under his own power, which is the still water concept, about 5 miles per hour. So this goes back to this information here. How do we write the rate Abram is going, the speed Abram is going in these two directions? So if he's going upstream, the water is coming towards him and it's going to slow him down a little bit. So it's his speed all by himself, which is 5 miles per hour on average, minus the rate of the current, which we've called C. Downstream, the water goes the same direction as Abram, so it speeds him up a little bit. So it's his speed in still water, 5 miles per hour, plus the water column we've called C. Then this column is where we use the information here. The time is equal to distance divided by rate. And so the time that Abram was traveling upstream is his distance traveled of 3 miles divided by his average rate of 5 minus C miles per hour. And his time traveled downstream is his distance traveled of 9 miles divided by his average rate in that direction, which is 5 plus C miles per hour. Then we move on to step 2. Step 2 says that we should use the time column to write an equation. That's because of this statement right here, that the trip takes him 2.3 hours. That's his total time. So we should understand that given the time he traveled upstream, plus the time that he traveled downstream, together that equals his total time, which we've been given as 2.3 hours. So that's how we write our equation. So we have his time upstream plus his time downstream equals his total travel time. Or also, we could look at that as his total time in motion. So we have 3 over 5 minus c plus 9 over 5 plus c equals 2.3. So now, solving this equation, which is a rational equation, we use our skill that we've learned previously. So we need our lowest common denominator, our LCD, which we should realize will be the product of the denominators of 5 minus c and 5 plus c. So multiplying each of the three terms in this equation by the LCD results in 3 times the factor of 5 plus c plus 9 times the factor of 5 minus c, and that equals 2.3 times both factors of the LCD. So now, multiplying this out and removing our parentheses, we get 15 plus 3c plus 45 minus 9c equals, here, multiplying the binomials together first gives us 25 minus c squared, and distributing the 2.3 will give us 57.5 minus 2.3 c squared. So now we should recognize that here we have a quadratic equation. Writing this quadratic equation into its standard form will give us 2.3 c squared minus 6c plus 2.5 equals 0. Now an equation like this, we should recognize, is very unlikely to factor, and so the best strategy here to solve this one would be to use the quadratic formula. So recalling our quadratic formula, our variable c would be equal to -1 times the b value plus or minus the square root of b squared minus 4 times the a value times the c value, all divided by 2 times the a value, where a is the 2.3, b is the -6, and c is the 2.5. So this gives us c is equal to -1 times -6 plus or minus the square root of -6 squared minus 4 times the a value of 2.3 times the c value of 2.5, all divided by 2 times the a value of 2.3. Simplifying each part in that structure gives us c is equal to 6 plus or minus the square root of 13, all divided by 4.6. So now, calculating each of those values separately, if c is equal to 6 plus the square root of 13 divided by 4.6, we get an approximate value of 2.1 to the nearest 10. And if c is equal to 6 minus the square root of 13, all divided by 4.6, we get an approximate value of 0.5 to the nearest 10. In both of these, given the context of c being the river current and neither one of these being extraneous value, it actually gives us two possible rates for the current, about 2.1 miles per hour and alternately about 0.5 miles per hour. So our conclusion should include both possibilities. So writing that conclusion and looking back for wording purposes, we're looking at how fast is the river's current. So for how fast, we can use the word rate, we can use the word speed here. So the rate of the river's current is about 2.1 miles per hour, or about 0.5 miles per hour. And it doesn't really matter in this context which one we write first. All right, in our second example here, we are looking at a riverboat travels at an average of 14 kilometers per hour in still water. So we have to recognize that as the average rate of the riverboat under its own power. Kilometers per hour being a rate unit of measure is one of the things that helps us identify that. We also then notice, it says the riverboat travels 110 kilometers up the Ohio River, so that would be our upstream distance, and 110 kilometers down the same river. That would be our downstream distance. So our distances are both 100 kilometers in this problem. Following that, it says in 17.5 hours. That would be our total time, which we'll use later on when we write the equation. And it says here, to the nearest tenth of a kilometer per hour, what was the average speed of the current of the river? So, same type of context here, or what we're solving for is the current of the river, the speed of it, its rate. We'll call that C. And so here, the rate upstream, where the water slows down the object, would be that 14 kilometers per hour minus the river's current of C. And downstream, where the water speeds up the object a little bit, would be 14 plus C. And then again, time is distance divided by rate. So this gives us 110 divided by 14 minus C, and 110 divided by 14 plus C. So our time column, along with the total time of 17.5 hours, gives us our equation. So we have the upstream time of 110 divided by 14 minus C, plus the downstream time of 110 divided by 14 plus C, equals the total time the riverboat's in motion of 17.5 hours. Now we move into solving this. So again, we need our lowest common denominator, and our LCD would again be the product of our two denominator factors, 14 minus C and 14 plus C. Multiplying each of the three terms by that LCD would result in 110 times the factor of 14 plus C, plus 110 times the factor of 14 minus C, equals 17.5 times both factors of the LCD, 14 minus C times 14 plus C. Multiplying this all out, we here would get 1,540 plus 110C plus another 1,540 minus 110C equals 3,430 minus 17.5 C squared. In this case, our linear terms zero each other out. This is a good example of a structure where our square root property would be probably the best strategy for solving it. The square root property yields 17.5 C squared equals 350. And then we'd have to divide both sides by the 17.5. And now we have C squared equals 20. And taking the square root of both sides, we get plus or minus the square root of 20. And understanding the negative doesn't make any sense in this context. The only valid solution would be the positive value to the nearest tenth, which is about 4.5, and that's in kilometers per hour. And then we have our conclusion. So the average speed of the river's current is about 4.5 kilometers per hour. And that ends this lesson.